We are here for Mr. Christopher Vanderlip's thesis proposal presentation. Chris, his committee is myself, Board of Analysis, and Chris came to us last year. He graduated with a bachelor's in geology from Grand Valley State University in Granville, Michigan. Does it sound like a nice place?
It's grand.
It's
grand and it has Grand Rapids as well.
But that's not the only degree he has. He's got a BS, or B, bachelor's anyway, in Spanish, and another bachelor's in photography. So he is multi-talented. And during his undergraduate research, he was involved in interpretation of coring in glacial sediments, and actually got an application along those lines. And he has a keen interest in glacial landforms and glaciology, but now he's just consumed with structural geology. So he's going to do a, what is the time limit, 23? I think I looked it up, it's like 20 to 30 minutes, 15.
40 or 50, I think it was.
No. And then he hopes to get feedback from the audience that will help him in his research. That's the spirit of these presentations, is to give constructive advice. So let's hold questions unless you want clarification at some point to the end. This is not where certain people have to leave. Everybody just asks questions. Chris, go ahead.
All right. Well, thank you, Dr. Cox, and thank you, everybody, for coming. So as Dr. Cox said, my name is Chris Vanderlip. My thesis proposal here is titled Eocene Paleostress Regimes at the Intersection of the Eastern Reelfoot Rift Margin and the Meeman-Shelby Fault. So I'm going to start off with a regional map. This is our area. Memphis is down here. Perhaps you've been there. Arkansas and the Mississippi River floodplain in the west, western Tennessee in the east. About 40 kilometers north of Memphis is Sugar Creek along the bluff line and the Mississippi River. So about a year ago, a little over a year ago, Dr. Cox discovered a fault there, and I immediately expressed interest in it. And things went from there. Before I get into the actual fault, though, I'm going to show you the Sugar Creek watershed outlined in red there. The star is the star on the main map. That is, sorry, point that out actually. The main map is the location of the principal fault exposure, the first fault exposure. The yellow outline is the map we're about to zoom into to show you that exposure, and then subsequent exposures. So Sugar Creek, there's a couple of tributaries. Sugar Creek is the main one going across the top there. And so the large star represents the first fault exposure that Dr. Cox discovered. So here's a picture of it with Dr. Cox in front of it, majestically for scale. You have blocky Eocene clay shoved over top of laminated sand and thin bedded clay. At least that's what I'm calling them, not being the sedimentologist here. Okay, so that's all Eocene strata. It is an apparent thrust fault. That's how we're interpreting it as of now. And so we look in the map up here, we have a second and a third exposure that were discovered in the creek beds. This one is in a creek just to the west of the first exposure. And so what we have here is this dark blocky clay over top of some Eocene thin bedded clay. And then down at the bottom there is this seam of coal that is truncated by the fault, and there appears to be no sign of it in the hanging wall. The third outcrop that we discovered is in a large tributary off to the west, a little bit further. So you've got this clay and sandy clay package in the hanging wall thrust over top of this succession of coal and sandy clay, some lignites, and then some silt. Again, there's this coal unit at the creek bed that is cut off by the fault and no sign of it in the hanging wall. So the three exposures define a more or less east-west trend to the fault, with the north side being a hanging wall, the upthrust, and the south side being the downthrown footwall. So in order to get a thrust fault to develop east-west, you need something, a maximum compressional stress, that's the arrows here, denoted by sigma 1. You need a maximum compressional stress in a more or less north-south direction. So that, unfortunately, or fortunately, is completely at odds with the modern east-west stress orientation, and also rather at odds with the Eocene inferred northeast-southwest compressive stress direction. So that leads me to my research questions. First of all, we want to know for sure, is this structure at Sugar Creek in fact a fault, or does it represent a mass wasting deposit? And by now, we're relatively sure that it is a fault, so that's the working hypothesis. So going on that assumption, the next question then is, what kind of sense of offset or timing of activity does it have? And then finally, the most interesting question I think for my thesis at any rate is that why is the orientation of the fault so wrong for the known and inferred stress fields? All right, so zooming out, I'll talk a little bit about the overall structure of the embayment, and then zoom back in towards Sugar Creek, you get a little more of the specifics. Excuse me. That yellow box there represents the regional map that I've been showing you, the larger scale with Memphis at the bottom and Sugar Creek there in the middle. The underlying structure of the Mississippi embayment, as most of you probably know, excuse me, is the Reelfoot Rift. And so here's the Western Reelfoot Rift margin fault and a pair of eastern faults on the Eastern Rift margin. You can see that the eastern margin basically goes straight through my study area. Now we'll look at the seismicity in the region. So each one of these greenish bluish dots represents earthquake epicenters. The main focus that you'll see obviously is the New Madrid seismic zone, and we're kind of off on the periphery of that. If you look at the eastern rift margin, you can see that there is some light linear sort of earthquake activity and even some clusters of activity near my research area. So the eastern margin does appear to be seismically active, and therefore, amongst other reasons, I believe that this is a worthwhile project, just for us needing to know as much as we can about potentially seismic structures, right? So back to my regional map here, I've got the eastern margin here. It is essentially a reverse fault with down to the west displacement that has been reactivated in more recent times with in a reverse sense. Did I say it was a reverse fault at first? I meant a normal fault. I think I might have said that. Anyway, it has been reactivated in a reverse sense and is now coming into sort of top to the west. As well, we have the Meeman-Shelby Fault here in the south, which is a kind of a similar situation where you have, I believe it's an old normal fault that's been reactivated. At any rate, it is top to the west sense, and so has been reactivated compressionally. The Meeman-Shelby Fault has not, to my knowledge, been mapped into Tipton County, but if you project it basically to the north, it comes straight through my area, and that means that my area is at the intersection of these two structures, hence the title. So it's rather geologically complex, which is kind of fun. Sugar Creek lies in between the Nodina and Drummonds 7.5-minute quadrangles. So I'm going to zoom in onto the Drummond's quadrangle in the south there to kind of talk about the physiography of the area. So the Drummond's quadrangle is outlined with the white square. In the west, there's the Mississippi River and the alluvial valley at about 70 meters of elevation in this location. You have in black the bluff line dividing the alluvial plain in the west from the uplands in the east. The uplands locally here are about 100 to 120 meters of elevation. So Sugar Creek is that drainage up there. It drains directly into the Mississippi River, as well as Bear Creek and some other smaller drainages. And then in this gold sort of line that I have there, that is a drainage divide, basically that separates the creeks over on the west side that drain directly into the Mississippi from those on the east side that have to go to the Hatchie River in the north and the Loossahatchee in the south before they make it to the Mississippi. So west of this drainage divide, you have streams with a very high gradient, and they're just cutting right through the bluffs, and there's all kinds of fantastic exposure. Really fantastic for western Tennessee, apparently. So I'm happy to have that. Let's see. Okay, so now I want to talk a little bit about the stratigraphy and then the timing, the way I understand it, of the activity on the Reelfoot Rift. So just broad brush, the stratigraphy consists of Paleozoic bedrock with Mesozoic and Cenozoic unlithified sediments on top of it. I believe it's about a kilometer's worth of unlithified sediments. The Reelfoot Rift was formed around the beginning of the Cambrian, somewhere thereabouts, and then time went by and it did whatever it was doing there, ceased being active, and was reactivated sometime in the late Cretaceous or early Paleocene. And so then it was reactivated in an extensional sense. You have extension, normal faulting, subsidence, which gives you an increase in those sedimentary units inside the embayment. And that extensional regime continues on well into the Eocene, up here, thereabouts. And somewhere in the Eocene, we start to have a compressional regime sort of take over. And that's about where my research area is situated, the fault is situated, I suppose you'd say. So I'm going to zoom in here to the local stratigraphy, the stuff that we actually see in Sugar Creek and that I'm going to be dealing with. At the bottom, so to speak, we have the Memphis sand, and above that is the Cook Mountain Formation, which is mostly clay and silt. These two, we don't know if either of them is exposed at the surface in the study area, but they are present at depth in some of the logs, well logs that I'm dealing with. So on top of the Cook Mountain is the Cockfield Formation, which we believe to be the majority of what's exposed at the surface in Sugar Creek and so forth. And the Cockfield is clay, sand, and lignite, so it's rather lithologically variable. On top of that, there's the Jackson Formation, which may or may not be present in the study area. And then on top of the Jackson Formation or the Cockfield, you have the unconformity represents something like 20 million plus or minus 5 of erosion and non-deposition before you get to the upland complex, which is sand and gravels. It is a Plio-Pleistocene terrace of the ancestral Mississippi River. Then on top of that, you have the glacial loess, aeolian silt derived from glacial materials that caps basically everything. And then inset into those various units, you have quaternary alluvium and stream terraces. So, getting back to the question of stress. The Eastern Rift margin, which I've simplified here, is shown in the modern stress field, the east-west maximum compressive stress, with Sugar Creek, of course, that, and Memphis is there. So the modern stress regime means that the Reelfoot Rift, or rather the eastern margin, is a right lateral strike slip fault, and this bend around my study area then becomes a releasing bend and an extensional sort of structure. So then in the Eocene implied stress field that is basically northwest, southeast, the entire rift margin becomes basically an extensional feature, hence you get that reactivation of the margin in the Eocene, Paleocene. Maybe Paleocene is better. Anyway, so that it's all extensional. So if we look at the stress field that the Sugar Creek Fault at the very least implies, it would be a north-south compression or maximum compressional direction, and so that would have a couple of potential implications. One being the rift valley, or the rift margin would be a left lateral strike slip, and then this bend here becomes compressional, which gives us east-west faulting in a reverse sense. At least that's what I think it implies. Brings us back to my research questions. Is it a fault? Assuming that it is a fault, what's going on with it? What's the sense of offset and timing of movement? And then, of course, the real question: why is the orientation of it so at odds with the stress field? So I hope to, I'm using and aiming to use fairly conventional geologic methods of mapping, bedding and fracture inventory, geologic profile, stratigraphic column, structural profile maps, contour maps, and then some geomorphic analysis. Mapping, I guess, is fairly straightforward. So bedding and fracture inventory helps us, we take the orientation of the bedding and the fractures and other qualities of the fractures that we can look at to show us age relationships and kind of unravel tectonic history. And so that figure here from Dr. Bartholomew's paper kind of showing intersecting faults and fractures arranged around a fold, and hinting, I guess, at the idea that those relationships have significance and can be used to interpret. I have here a sample geologic profile. It's preliminary. It looks fairly complicated. All the colors on here are basically just lithologies. You can probably just disregard those for this illustration. QAL, QL are the Quaternary alluvium and loess units. These are from lignite logs, coal exploration logs, I should say. Excuse me, so that's QL and QAL. PUC is the Pliocene upland complex, and then ECF being the Eocene Cockfield Formation, which is the bulk of what I've interpreted these to have. But it appears that we have some Cook Mountain down on the bottom of a couple, and between these two wells, the Cook Mountain contact changes vertically about 30 meters in a 5-kilometer span. So we can potentially use that to infer a fault, or I guess fault is basically what I'm saying. Preliminary, of course. Anyway, so, and then from the elevation data, we can construct contour maps. This is just a sample contour of the Cook Mountain from Richard Martin's thesis. We've got a couple of wells here that are fairly far spaced apart, and there's more or less, 10, 15 meters of change, and then you get to this little small area, which is in my study area, and you have a bit of a larger change in a smaller area. At least that's how I've interpreted that. Anyway, so geomorphic analysis. Sugar Creek has a couple of fairly well-developed terraces I'm calling T1 and T2. The T2 is about 7 or 8 meters in places above the actual creek bed. And so if we look at longitudinal profiles of terraces, they can cue us into some potential tectonic activity. I have an example profile here from Holbrook and Shum. Basically, it's just elevation and valley distance, down valley longitudinal distance. The red line represents the expected concave profile that you get, that the idealized river has. And so we can see these convexities in the terraces, And so that suggests that the terrace, having formed horizontally may have been upworked tectonically. Of course, it's not, an absolute indication of tectonics, but it's a way to sort of get at that. As well, we can look at things like stream incision. Sugar Creek has a number of hanging valleys and nick points like this. Unfortunately, I'm sorry, there's no scale there, but this is that second terrace, and you're looking at 4, 5, 6 meters, maybe even, probably not quite 6, but significant. And so I want to look at the distribution of those hanging valleys, see if they're restricted to one side of the fault or not, because those could potentially represent a tectonic disturbance making its way up the watershed. Let's see. So I guess then to wrap it all up, I've got my timeline. As far as summer and fall are concerned, we've been doing mapping. So I'm continuing into the fall semester, October through December, drafting and refining cross sections and maps, continuing to map, field checking, stratigraphy, and stream terraces, refining those maps and cross sections, like I said, getting into the beginning of next year, drafting final figures, making those last field observations, starting to write my thesis, into February and March doing more analysis and just kind of wrapping everything all up, and then I plan to submit and defend my thesis in April. So that's what I hope to do. Thank you.
Questions or comments for Chris?
Yes, sir.
When you hung your well logs, what was your data?
Basically, it was a common, it's well number 18, which is at about 100 and, I've actually got it in there, 120 meters roundabout, 117 meters, so that's, oops, that's 117 right there, that's that well 18.
So what's that 117?
117
I guess it's
meters,
just
that's the top of that particular well, and that's just where I arranged those from. Dr. Van Arsdale?
Yeah, you pointed out that it looks like there may be some earthquakes occurring along the Eastern Rift margin. I realize they're small. Do you have any focal plane mechanisms to support thrusting in your area or in that margin?
I can't say I know whether or not they do support thrusting. I think most of that analysis or that conclusion comes from a lot of the stratigraphy that is down thrown low and then up thrown higher along the faults that are implied through seismic and well logs as well. I know there are some focal mechanisms in the area. I have not looked closely at them, so I probably should.
As I recall, there aren't any right there at Sugar Creek where that bend is.
I just wonder if they can be visited. Is it possible to have someone look at those and provide a focal mechanism, or is this just too small? Maybe that nobody's attempted to do it. Not that it's something that falls within, but you might be able to get somebody that's seriously interested in doing that for you.
No doubt.
The second question I had was, I think by convention typically, maybe not, but I think when you're labeling your terraces, T1 of the implication is that they is the oldest. I should be careful saying that.
Some authors do it that
I've seen
way,
both conventions.
mainly in the older literature, but you really run the risk of getting your numbering all messed up when you discover a higher terrace.
Yeah, that's true.
And in the newer literature, 1 is the youngest, or 0 is the modern floodplain, 1 is the next terrace, and then that really makes a lot more sense. But in the old literature, it is that way.
And I guess where I was going with that was that there's been work done in the area, so you may have to make sure you clarify that as you write it up, how you're doing your numbering scheme. Because there are old papers out there that I think number the other direction.
Yeah, and I guess I could, take a look at Sausier's work. He did work on the larger rivers along the bluff line, but some of those may or may not coincide with some of the terraces, and I guess if they did coincide, then that could suggest that, you know, there's not really a seismic interpretation of why there's, why, you know, the discrepant or the large downcutting. And of course, you know, the Mississippi being right there, downcutting is what you expect. So there are definitely other possibilities involved in that. Thanks, good questions, I appreciate those. Good thinking. Yes.
It looked like, you know, the fault, the reverse fault that you show in the pictures is not too far, it's very close to the surface, right? It's not too.
Right, yeah, they're exposed, you know, in a creek, so they're all within the, you know, 10 meters above the ground surface there.
10 meter.
Mm-hmm.
Yeah, how do you relate those, you know, especially for the inside stream or Hayne Valley you mentioned, you know, how those nick points,
Mm.
you know, relate to, you know, from the geomorphic point of view, you know, I relate with your study on faults.
Well, okay, so like if you have your, we'll just say that's your, you know, your land surface, and then you have some uplift, and so you've got part of it that's up like that. Now you have a steeper gradient to rivers that would be on there, and so at some point in their sedimentation they would start to cut down, and the idea is that, you know, the rivers advance by headward erosion, so they're kind of scooping out the nick point and scooping and scooping and scooping. So that can, among other things, I have to be careful obviously, but that can kind of show that there's something going on there. Does that answer your question?
Yeah, I think what I was going to refer to is, I know Mike Barnhart, one of our former colleagues, he did a lot of erosion studies. The gully erosion, and they study those gullies and some structures
Mm-hmm.
in the Meeman-Shelby Fault area, which is south of what you,
Yeah.
what you talk about.
Yeah, so I should probably look into that. Appreciate it. Yes, sir.
Yeah, I would just tell you, you need to be careful about you have this so-called bend.
Mm-hmm.
Probably doesn't do that. When you say there's a releasing structure, it's not a bend. It's really two different faults that are interacting.
Mm-hmm.
And so you probably ought to put together an idea of how the structure actually evolves. So where you see it as a strike-slip fault, and then you're going to see an extensional faulting event. And you should be able to sort of trace those upward too, and when it converts into a compression type event. So that you get a good idea of exactly what's going to happen as you follow the structure up.
That,
Indeed.
related to Dr. Barthelme's comment, that eastern rift margin is really poorly constrained. We have good coverage to the north with Parrish's work, with the seismic lines, and then of course we've got power data at Memphis. But that area where you are in between, I'm not, I have to look at it again, but I'm not aware that we have any really good control other than gravity and magnetics as to what that rift margin is doing
Right.
through your area.
Well, one of the down lines goes
That's what I was just gonna mention.
right down
Goes
the
right down that road.
right by the fault. I think you gave him the line.
144E,
144.
which didn't get published in the paper that the two.
That was the one that we thought that was going over Pluton, I believe.
Right. Yeah, and I've taken that one. I don't have a figure for it, unfortunately, at least not here. I've taken that and, you know, roughly lined it up as well as I could to constrain it with the topography you got and what goes along that road. And basically I know roundabout where the two of you, or whoever interpreted the rift margin faults there, and it's not terribly far off of what we have. Wow, this one there,
I wasn't surprised.
The problem is the fault strikes almost parallel to the line. That's the problem.
To the Dow line we was
Yeah.
talking about? Yeah, I remember being something about that line, that maybe because we didn't illustrate it because we we weren't quite sure what to do with it, but, so you're saying that where the faults are in proximity to your star fits the Dow data quite well?
Fairly well, yeah. I think if I recall correctly, so if you've got this one, I think it came actually a little closer, and this one came a little closer in there.
So they were north-south lines?
No.
No,
Are you talking about where
right,
the faults are?
where the
Okay,
rift
right.
fault comes through there. Yeah, the fault line runs basically, or the seismic line runs basically through there, and then up this way to Covington, which is somewhere in that vicinity. So it seems to line up pretty well. I mean, I don't know how much.
Why don't you go to your early LiDAR figure that zoomed right in on the site? No, oh yeah, right there. You see the road in the LiDAR? That's where the line went. So that's how close it is. And the fault should cross the line, because it should cross the road right there.
And in that line, there is a fair degree of complexity in the Sugar Creek area.
Yeah, but you don't have anything that shallow.
Right.
To resolve.
Dr. Johnson had a question. Do you still have?
It's unrelated to any of this, so if you still have questions about that, you should.
Okay. Dr. Lumsden?
You go back to the previous slide that you had up there.
No.
I don't blame you, I would do it.
Where was it?
Right there.
Right.
Is it, it's striking me, the Mississippi River is coming straight south and then makes a 90-degree turn. Is that
Yep.
coincidental, or is that just got something to do with?
You know, I wonder, and this is purely spectacle. Yeah, the word I'm trying to come up with is escaping me.
I think it is spectacle.
Speculative. So, right, if the rift fault actually does this kind of thing here, there's a small drain, or actually it's not really small drains, but kind of does a sort of hook pattern right there, and this does that sort of a hook pattern, and I keep drawing lines in the topography going, what is this hook thing? Is this my imagination? Like I said, it's purely skeptical.
How much does the Corps of Engineers have to do with that north-south channel?
That's a good question.
Is that
They no
natural?
doubt have something.
Because obviously the historic cutoff, the historic channel is that big bend to the west.
Yeah.
So that's nothing that's very long lived.
Yeah,
But
I
you still
really
have
don't know.
you still have the older channel making a giant loop up to the northwest too, though. You know.
Yeah, the older channel does some really weird things through there.
Another interesting thing that I'm sure that I know that you're well aware of because we've talked about it, was your fault and your topography argue against the landslide because your Mississippi River bluff is on the north side, and that's the hanging wall. So you would expect it to go towards the Mississippi if indeed that was, of course, you're looking at today's topography and yet you're looking at Eocene structure. So
Right.
that's kind of that argument. Is
Yeah.
Well,
the
even in
fault
the
was-
Eocene,
but if it's
you
real
go generally
young,
lower
real
topography
young.
and higher
Yeah.
topography,
But
lower topography that way in the northwest.
Do you have any chance of seeing whether the upland complex is displaced by this? Do you think you're going to have any?
We've not
kind of
located it. Actually, let's see, I have a couple of extra slides at the end here just in case they came up. There is actually an unconformity there. So there's Dr. Cox in front of this unconformity where you have this tilted Eocene strata and above it subhorizontal. So this intraformational unconformity, or at least that's what it looks like. We're not, Dr. Larson wasn't 100% convinced, but we haven't really looked closely at it. That's what it looks like anyway. But it also kind of rises as you get closer to the fault. So maybe this is something having to do with initial normal movement and then reactivation in a reverse sense.
Now, isn't this in line with the incline feature too? You haven't mentioned that. at
No,
all.
I haven't, because I'm basically going on my proposal, which was before we discovered the anticline, but I do have some slides in here. Is it before or after? No, after. Speculation on that. Okay, here we go. So this is off to the west of Sugar Creek. Sugar Creek runs up. So you can see the point now, it's up here, off over this way is where Sugar Creek is. And then this is a quarry, gravel quarry, where we've got an anticline with a shallowly dipping limb there and a steeply dipping limb there, shallow and steep being relative terms, of course. And the anticline trends about 110 degrees And so, and actually, I'm going to show it. So that there's the anticline, and there's, you can see the way it's going. We've got this quaternary lust drop down into, or at least I think it's lust, drop down into this. So this is potentially a younger structure, or maybe the Sugar Creek Fault is younger and has been recently active. In any case, so it's trending off to 100, 110 degrees, and if you look at that, it basically goes straight into right where there's this nice straight part of that that creek bed over there, and it may or may not be related. We have not, no. This is so intensely vegetated right now. I can't imagine anybody's been through there forever and ever and ever. But it's definitely on my bucket list. Like absolutely, positively, we have to get there anyway because of the EdMap project. But I really feel like because you're looking at this is, I don't have the elevations on here, but this bluff here is really steep, and there's some really nice scoop river cutbank, thank you, exposures, and assuming they're not completely vegetated, which I don't think they will be, should have some exposure, and it'll be really interesting to see what's in there.
Maybe the best way to actually figure out what's going on along the western margin there is actually walking along that creek and verifying structures, as long as landslides haven't
Right.
Complicated it too much. Obviously, there's landslides all over the place.
All over the place, indeed.
Chris, what kind of joint data have you gotten out of those drawings?
I have joint data. So we've got joint data on the anticline. I've got lots of joint data from the creek, from Sugar Creek, and I didn't include any of it in here. I don't have it in any of my extra slides either, unfortunately. But there's a few trends. But if you look at Sugar Creek and you look at the anticline, you have a northern sort of trend. I think it's just a little bit, what would that be, west of north. And admittedly, I've been using the whole bow tie thing, so I don't have really much more specific than that. But there really does seem to be a fairly strong north-south trend in the fracture data that we have thus far.
So do you have any budding relationships?
Unfortunately, very few that there's been a couple that I've noticed here and there. I don't know how much stock to take in them. There's definitely strong fractures, but as far as it's all unlithified, so there's no mineralization. We haven't seen any. We've seen one slicken line, I think. So unfortunately, the fracture data thus far, we don't have a whole lot to go on beyond just the orientation, but hopefully I'll be able to interpret or look at.
If you have those thrust faults, can you find anything that indicates direction of movements or lines on it?
Not that we've seen.
Are they sands or clay?
Sands and clays. Mostly clay in the exposures that we've got, but it's clay and sandy clay. A lot of it's clay and sandy clay. There's some really nice sands in the footwall. The very first exposure I showed, it's up, thrust over some sands, but most of the hanging wall stuff that we have exposed is clay and sandy clay, like I said. We haven't seen any slicks or anything.
Probably need to dig further back.
Probably.
At 2 or 3 feet, and you're only going to have, even if you're looking at alignment of quartz grains, you maybe only have 30 seconds of examining the fresh exposure before it disappears. So, that might be a way to get some additional data.
Certainly.
The one slick insights we saw was after a heavy rain, and we were walking, and the outcrop fell off, and you saw the slicks, and I don't know how long they lasted. But it wasn't on the main fault. It was on subsidiary wall fractures.
Right, and so we've done a little bit of digging at the faults to try and see what we can see, and trying to get more precise strikes and whatnot. And so we haven't seen anything yet, but it definitely, I think, bears investigation, further digging further into those exposures to see what there is, if there is anything that we can examine. Haven't seen anything yet, unfortunately, really. Anybody else? Johnson?
Thank you, Chris.
Thank you.
Lots of food.
Got some donuts.
I was just curious about the mass waste.
Mass wasting.
And why